All right, how's it going, everybody? We are here on Monday of week 8, and we are today going to wrap up the topic that we kind of left dangling at the end of week 7 here. At the end of last week, we were talking about the central limit theorem, and I didn't really get into any of the exciting examples or talk about any of our kind of our hypotheses that must be met associated with these guys. So we want to look a little bit more closely at this guy today. We'll wrap up this topic here in chapter 7 today, and then we'll look at our introduction to chapter 9, which is finally getting into our statistical decision making that we've been kind of, in a sense, waiting for all semester. We've been building up a lot of these computational techniques so that we can help inform the decisions that we want to make starting tomorrow. So what I've got up on the screen right now is the wrap up to last week's video here. This was some, you can see the handwriting is already on the document here. These are some of the things that we had written last Tuesday. So let's kind of refresh where we were here, and we'll pick back up with this document here. We'll also look at a bunch more of our technology computations here today. In one of our wrap-up examples last week, we were looking at adult male height and its distribution here. We'll use that again today so that we can keep on having a good grasp of some of the values that we should be expecting here. And what we'd been discussing, and this is some information that we've seen a bunch of times by now, our normal distribution is always indicated with the capital N, always the average and the standard deviation term in that order in the parentheses afterwards. Talking adult male height has an average height of 68 inches in the US with a standard deviation of 2.5 inches. However, and when we talk about the sampling distribution of the sampling means, we're going to get a little bit of a different distribution. And our difference here is this. This is one single observation X. That's one person being observed and talking about their heights. When we move on to our sampling distribution of the sample mean, that means that we are collecting the sample mean over and over and over again. So this is saying you're not sampling one person, you're sampling 30 people and getting their average height. The average height is the variable of interest to us, not the 30 people. Well, as we discussed last time, it's a lot harder for a group of people to collectively deviate from average all in the same way. That's very rare. And so what we're going to see here is when we talk about our distribution of the sample means, if we were to take lots and lots and lots of samples of maybe 30 individuals and find their averages, we should find the averages have a harder time deviating from the true average than an individual observation will. It's easy for one person to be weird. It's hard for 40 people or 100 people to collectively all just happen to be weird in the same direction here. So what we're seeing is if we're going to look at, for example, taking groupings of 100 adult males at a time, then we should see that their average height, x bar, is distributed with a much smaller standard deviation than an individual is, right? So we're seeing that our groupings of 100 people at a time, they're still going to have an average height centered around this 68 inches. It doesn't matter if you're taking one person or 100 people or 1,000 people. We should always expect our average height to be 68 inches because that is the average height of one individual. But the difference is here is that we're seeing that our ability for groups of 100 to deviate from average is smaller than our individual's ability to deviate from average right here. The 2.5 got reduced to a 0.25 because we divided by the square root of the sample size in each grouping of the average. The more and more and more people that we sample, the bigger n gets, the smaller our standard error term. So instead of calling this a standard deviation term, since we've sort of modified it, it's really the standard deviation divided by the square root of the sample size. This is now what we call a standard error term. So here I'm saying the standard deviation associated with the sample means, not with the individuals up there. So again, the big distinction to make is that up top we're talking about individuals, one person at a time. Down here we're talking about the average height of 100 people at a time, or at least n people at a time right here. And so what that's going to mean is our average stays centered at the same location, but it's harder for a group to deviate collectively in the same direction on average than it is for an individual. So we should always expect to see this reduced standard deviation term here. So then we answered two questions before we wrapped up. We looked at one person, so not a group. So it's easy for them to deviate from the mean. It's just one person. And we saw that this one person was 2.5 inches away from the mean. And when 2.5 inches away, when we are 2.5 inches away with a standard deviation of 2.5 inches, then that is exactly one standard deviation away from the mean. And we did our little Excel computation here to get the probability associated with that. Not super weird for us to find one person taller than 70.5 inches. That's just 6 feet tall and a half an inch. Not that weird. 15.87% of people are at least that tall. On the other hand, if we were to group together 5 people, remember that it's a lot harder for us to random, or not harder, it's more unlikely for us to randomly sample 5 people and for them to all collectively deviate from average in the same direction here, all of them being a little taller than average. So what we're seeing here is that based on our reduced standard deviation, it's the standard deviation of the original, 2.5, divided by the group size of the averages that we're collecting here. 5 people at a time are being averaged. Then in this case, we see that we have this much smaller standard deviation, much smaller standard error term to work with right here. Notice our computation stays the same. It's still z equals x stuff minus mu divided by sigma stuff. It's just that in this case right here, our x stuff is now x bar because we're looking at the average height. The average height is going to be taller than 70.5 inches. And our standard error term is smaller than the 2.5 inches because we've divided by the square root of 5. So we've got that 1.118 here. So what we're seeing here is that where being 70.5 inches for one person is that one person being one standard deviation away from the mean, we're now seeing that 5 people's average height being 2.5 inches above average is actually more representative of about 2.25 standard deviations above average because it's harder for 5 people to collectively deviate in the same direction. When we computed this probability here, we found that there was only about a 1.27% chance of seeing 5 people randomly selected on average, 5 males on average randomly selected having a height of at least 70.5 inches. So it's much, much less than the 15.87% associated with just one person right there. And then finally, we said, all right, what if I actually took 50 people here? Well, 50 people is going to reduce our standard deviation even further. We saw that if 50 people had an average height of 70.5 inches, that would be equivalent to us being at a little bit more than 7 standard deviations above normal, which is an incredibly rare event. Super, super, super rare. So when we went to compute the probability, I think that, oh no, Excel did eventually give us a number there, right? We got this, insanely small percentage that we're observing right there because it's very unlikely that you are going to randomly select 50 individuals from a population and find that they pretty much all deviate from the mean in the same way. In fact, if that were the case, then you should be maybe saying to yourself, did I really think that 68 is actually the mean? If I can sample 50 people and get their average to be 70.5 inches, maybe that's suggesting to me that 68 was actually wrong as an average right there, right? Rather than us believing that we got some event that's this unlikely. That conversation that I just kind of phrased up right there, that's exactly what we're going to talk about starting in chapter 9 right here, is saying to ourselves, when we see events that are this unlikely, this is probably better evidence to us that our original distribution was wrong than it is evidence that we just got wildly, wildly unlikely and drew such a rare sample like that. So instead of just believing that that's just the event that I got right there, this is so unlikely that this would actually probably for me be evidence that this is probably not true, that this distribution of adult male height has to probably be wrong. Otherwise, there's just no way that we'd be seeing results that are like this, right? So that's exactly the conversation that we're heading into in chapter 9 here, which is why I wanted to phrase that up that way. So let's pick up where we left off right here. And by the way, I have to lay out my uniform distribution joke right now. I am currently waiting on a furnace repair person to come. They were telling me that they're going to be at my house between 8 and 11. It is currently 10:45, and so I am wondering what is the probability if the repairman is likely to come at any time between 8 and 11. Well, that's 180 minutes. And I just observed, so we've got from 8 until 11. Looks like because this is 180 minutes, this is going to be 1 over 180. I am interested in the probability it comes after 10:45 because that's right now, and that's going to be a 15 divided by 180 right there, which should be 1/12, right? which is what, 8.125. So, unfortunately for me, I've encountered the 8% probability that I am going to probably have to get up during this video right now, since I am certain that oh, I'm not certain. At this point, I'd rather it just comes tomorrow or something like that. In any event, I might have to stand up here in a minute because I got a furnace repairman allegedly coming in the remaining 15 minutes of the time interval that he told me he'd be here. So here we are back at the central limit theorem. So here's where we're at. What the central limit theorem is telling us is it informs us how to make our adjustment from x's distribution to x bar's distribution, the distribution of the sample mean, the mean of a sample. That's what we're looking at, the distribution. Not the distribution of individuals, but the distribution of averages of individuals, an average of n individuals in particular. So the sampling distribution of the sampling mean, we're given this information by the central limit theorem. The very cool thing about the central limit theorem is that this applies even when the underlying distribution is not normal. And this is where we get this idea that the central limit theorem helps us see why the normal distribution crops up in so many places, right? So on the one hand, tons of things are naturally just normally distributed, right? Individual observations, especially in lots of biological things, it just so happens that things are all normally distributed. Not all things, but so many things are normally distributed. But what the central limit theorem is going to show us is that even variables that are not normally distributed, if you take groups of them and average the values of those groups, you will find that your averages are normally distributed, even if individuals' outcomes are not normally distributed, which is very interesting here. And so I'm going to show you some examples of this with technology here. And so rolls of a die, we know that these follow a uniform distribution where there is an equally likely chance of any given roll between a 1 and a 6. By the way, it's going to matter in a minute here that we identify that this uniform distribution is one of the weird ones because most distributions we think of as either being associated with discrete variables or continuous variables. Binomial is very much discrete only because it's always just two choices, right? True or false, male or female, 1 or 0, heads or tails. Whereas the normal distribution is always used only continuously. We think about things like heights as being a continuous breakdown. The uniform distribution is one of the only, not the only ones, but it's one of the few where there is both a uniform version and a discrete version. Here we're talking about dice rolls being discrete because there are 6 possible outcomes, 1 through 6 whole numbers only. I can't get the values that are in between. However, me waiting for the furnace repairman time up above right here, this would be continuous because he could show up at literally any time that there is between 8 and 11 right there. So this would be a continuous uniform. Here we're looking at a discrete uniform with the dice rolls. And what I want to do is I want to show you with technology kind of how some of this stuff pans out right here. So I'm going to pop on over to a little bit of code that I have pre-written here before the day. It is not at all important that you understand what this code is actually doing, but I want you to be able to kind of vaguely see it. I don't think there's anything too crazy here. You guys have already seen a little bit of this stuff right here, so hopefully this isn't too crazy. At the end of the day, all I'm using my computer to do here is to roll the dice and then group up my dice on average and then make plots of them all just quickly. So I've just done this. So it's all already put together here. So this first box right here with these import statements, this isn't much to worry about. This is just me getting help from some external libraries. Python does not have built-in the ways to handle all these things. So there's some external libraries that we get some help from. This next box right here is going to do a little bit of dice rolling right here. This is going to say from the NumPy library, grab the sub-library named random. From that sub-library, grab the function called random integer, right, randint, and it's going to grab us some numbers between 1 and 6. Unfortunately, Python does this weird thing where it includes the lower bound, but it discludes the upper bound. So this is really going to give us from 1 to 7. And this says, roll for me 10 dice that are going to be between 1 and 6. And we can see when I do this, it gives me some dice rolls. This hopefully looks to you like a believable list of 10 possible dice rolls right here. And I can do this more than once to maybe help you believe that we're not going to see any 7s in there, because I know that seems kind of weird right there, the way that's phrased. But this will get us just values from 1 to 6. Here we go. 1s, 2s, 3s, 4s, 5s, 6s. So What I'm more interested in seeing is what happens when we roll a die many, many times. Now, what we know about rolls of a die is that they are uniformly distributed, and I know that uniform distributions have that flat-topped shape, that rectangular shape right here. So what I'm going to do is I'm going to roll that one die 200 times. I'm going to save my results as what I call as rolls one, and then I'm going to do a plot of that data right here. And I've got a fancy built-in function that's going to kind of do this plotting stuff for me. So, and I'm going to tell you before I do this thing's doing one small stupid thing to me, but we're still going to be able to see what we want to see right here. What this is giving me is it's giving me both a histogram and a curve associated with this. Ooh, and this one doesn't look super uniform right here. I want to show you that the stupid thing that's happening to me here is you should notice there was only 1, 2, 3, 4, 5 columns being made, and that this fifth column seems to be about twice as tall as the rest. For some reason, just in this one case here of just the rolling one single die, it's lumping together my final two columns as one column right here, but it's at least making the interpreted smooth curve is appropriately following the fact that these should be split up into the two columns right there. But this is even kind of surprisingly weird to me right here. I was expecting it certainly to be a little bit more flat-topped here. Let's roll 200 dice a couple more times and see what we get. Ooh, seeing some kind of stranger ones right here. Okay, that's maybe a little bit more like kind of what I'm expecting right there. I'm seeing this, again, the more flat-topped, uniformly distributed shape here. So the cool thing about this graph is it's giving us both the histogram and sort of the interpreted curve that's associated with the histogram. And so what we can see right here is, oh, that's a very nice and consistent one right here. And again, we're seeing that the continuous curve that's mimicking the discrete histogram is looking very similar to that flat-top shaped curve out there. And again, we know that there's always variability in our randomness out there. We're never going to get anything perfect, but this seems pretty close to me to evenly splitting those results. And it does look like this final bar right here is not quite twice the heights of the others, which is why I'm seeing that little dip down right there. So the point is this. All we're doing right now is rolling one die, and we are seeing uniform results. That is not a bell-shaped curve right there. That is much, much closer to our rectangular-shaped curves than our bell-shaped curve. Now let's move on. Now we're going to roll two dice at a time and get their average roll. And we're going to roll this a whole bunch of times, right? So I'm going to write a function here that rolls the six-sided die n times and then divides by n. This is going to get the average roll of n dice per roll. Now what I'm going to do is I'm going to roll two dice. I'm going to get the average of two dice 1,000 times, and I'm going to plot this guy. Now we've already done this one also. We've already looked at the outcomes that we expect to get from rolling two dice. And what we're seeing here, and by the way, it's doing some kind of stupid things with my histogram, but it's doing smart things with my curves here. What we're seeing is we're getting this very pyramidal shape right here. And we did exactly this. About 2 weeks ago, 3 weeks ago, we looked at our uniform distribution for rolling one die, and then we graphed our probability distribution, our histogram associated with rolling two dice, and we saw that we were getting things like a 1 in 36 chance of rolling a 2, a 2 in 36 chance of a 3, a 3 in 36 chance of a 4, and we saw it linearly increase until we got to that 6 out of 36 chance of getting a 7, and then that linear decrease back down again. So don't worry about these like gaps in here. It's just having a tough time with the fact that this is a discrete breakdown right here. But notice if I do this over and over again, I re-roll my two dice 1,000 times over and over, and we keep on getting this pyramid-shaped curve right here. And very importantly, notice this is not a bell shape, right? A bell-shaped curve had a concave down section first, and then it had concave up sections on the bottom. This is very much more like these two straight line pieces right here. So notice what's happening here is that we went from a flat-topped distribution when it was one die, the average of one die, which is just one die. Then it sort of transformed into a triangle for two dice. Now what happens if and maybe let me just do a couple more of these here. What if I did three dice together? Well, three dice together is kind of looking triangular still here. And I'm just going to change some of these names in here. All right, what if we go to four dice? Well, it's maybe looking slightly less triangular here. Notice that I'm seeing a bit of the tail develop down here. The tail develop down here. Rather than a just like straight line approaching the x-axis, it looks like it's rounding itself out. Also on top, it looks like it's kind of forming a rounded top instead of just a sharp top up there. So that's at four dice at a time. What about with 5? Well, 5, I'm still seeing that same tail here. Ooh, that one got weird. Holy cow, we got a whole bunch of one result right in there. Notice it's still got a good bit of the triangularness to it, though, not the bell-shaped curve. But if we keep on bumping this up, here's 6. A little more bell-shaped. Here's 7. Oh, now we're getting bell-shaped out there. 8. Okay, that one looks still maybe a little bit more triangular here. Okay, let's bump this up. Let's see if we take the average of 15 dice at a time. Well, now this is starting to look more like this bell-shaped curve to me, right? So here's the strange and surprising thing that's happening. We're starting with a variable that has an underlying distribution of not a normal distribution. It's not bell-shaped, it's a flat top. This is supposed to be a rectangle here, right? We're starting with a rectangle-shaped distribution when we look at one observation at a time. Then when we look at two observations at a time, our rectangle shape turned into a triangle shape. That's also weird to us, right? This is the average of two rolls, and we did 1,000 sets of two rolls and took their averages, and we're getting triangles out here, which is a little bit weird. Now, as we increase more and more and more, we're seeing that the larger of the group size that we're getting, the more our resulting distribution of averages is getting closer and closer to something that looks like it's normally distributed here. So even though the underlying distribution here is a uniform distribution, when we take groups of 30 on average, our averages are normally distributed, not uniformly distributed. We're not equally likely to get any possible outcome when we look at the average roll of 30 dice. It's very hard for 30 dice to have an average that's far away from the 3.5 that we know to expect, because it would be very strange to see 30 dice all collectively deviate to be larger than average or lower than average out there. And finally, if we get real big out here, if we do 100 dice at a time, right? So this says roll 100 dice and get the average of those 100. Then do that 5,000 times, right? So this is officially us rolling 500,000 dice right here, grouping them in groups of 100, and that means that we've got 5,000 groups of 100. And now what we're seeing out here is some very bell-shaped curve distributions, right? This is very close to looking like a normal distribution out here. We certainly have some tails. We certainly have a rounded top going on up here. And so this is kind of interesting, right? What we're seeing here is as our sample size gets larger and larger, the distribution of sample averages becomes normally distributed regardless of what the parent distribution is. This is all data that's coming from a uniform distribution, rolls of a die. But rolls of a die on average will be not uniform but normally distributed when we look at their groupings of many of them together. Now, one thing before I kind of walk away from this setup is this. What we're seeing here is that one die at a time is not normally distributed. This isn't a bell-shaped curve. 2 dice at a time, not normally distributed, not getting a bell-shaped curve. Even when we did like 5 dice at a time, we were still getting some kind of like pretty janky looking things here, right? This, we're seeing really no essentially tail out here. This is still basically just coming down and dying. At top, still looking a little bit weird right here. Some of these kind of maybe, but for the most part, I'm pretty weird to even call this one normally distributed. So one of the things that we're see again, here's our this is really just like a fancier triangle right here when we roll the 5 dice at a time. So one of our important takeaways here is that the central limit theorem says if you're going to take groups of individuals and find their average value, the averages are likely to be normally distributed, even if the original distribution is not. But it takes a couple observations for that to happen. For example, just taking groups of 5 on average doesn't seem enough for us to get into the stance where we're now experiencing a normal distribution of these sample averages. A pretty typical thing is to say, and this is a very soft rule right here, a typical thing to say is that we typically need to see groups of at least 30 before the group average can be expected to be distributed normally. And we see a pretty decent bell-shaped curve right there. So our typical statement with the central limit theorem is this. The sampling distribution, the distribution of samples, of the sample mean, when we look at the average of groups, is going to be normally distributed regardless of the distribution of the parent distribution. Here the parent distribution was uniform, not normal. as long as we have taken about at least 30 groupings, or excuse me, 30 individuals per group, then the group's distribution should be approximately normal here. And the reason that helps us is because this gives us a central distribution from which to measure everything here. All right. So what I want to do now is come back to this guy and see if we can talk about our probabilities here. And I think this is just us. Okay, so let me come back to Microsoft Word here. And let me kind of talk through some of these scenarios here. So the central limit theorem applies even when the underlying distribution is not normal. We're looking at a discrete uniform distribution, not a normal distribution. So we know, we've talked about this many times before now, our average roll of a single die is 3.5, right? You never will roll a 3.5, but if you average 1, 2, 3, 4, 5, and 6 that are all equally likely, you get a 3.5. We know that one roll of a die at a time will follow a uniform distribution. One roll is equally likely to be anything 1 through 6. So when we roll, so let me kind of fill in some values here to answer some questions. When we roll a 1 die and compute the mean of the roll, what is the expected average of our roll? Our expected average is going to be 3.5. That's our I guess of our one roll right here, I'll call that an X bar because that is our sample average, not our population average. We expect our sample average to match our population average very typically here. What is the probability that our average roll is 2 or less? Well, the probability of 2 or less is the same thing as the probability that X is 1 or 2. So that is a 2 in 6 chance. I can compute that exactly. I know my uniform probabilities. There's 2 out of 6 rolls are 2 or less on a die. I don't have to do anything crazy with that right there. All right, so now we're going to roll 2 dice, and we're going to compute the mean of the rolls. What is the expected average value of our roll? Well, if I'm rolling 2 dice, my average value I expect for the first is a 3.5. The average I expect for the second is a 3.5. I add them together, that's 7. Divide by 2. I'm expecting my average roll to still be 3.5. That hasn't changed. What is the probability that our average roll is 2 or less? Well, I can kind of do our same thing here. Probability that we get a 1 or a 2. Oh, wait. Okay, 2 or less. There is no way. Oh, I'm just confusing myself here with our. So if my average roll is a 1, then that means that I got a 1 on the first and I got a 1 on the second. That should be a 1 in a 36 chance right there. If I'm going to get an average roll of 2 or less, this would be me getting a 1 and a 2, a 2 and a 1, or a 2 and a 2. There are 3 ways for me to get an average roll between 1 and 2. So there's a 3 and 36 way. So it looks like I'm going to get a 4 out of 36 or a 1 and 9. So the thing that I'm seeing right here is that it's harder for us to get 2 dice on average to be extreme than it is for just 1. It's not weird for 1 die to have an extreme result. It's weird for the collective average of several dice to have an extreme result right there. Now, we roll 20 dice and compute the mean of the rolls. Well, I'm still expecting my average die roll to be 3.5. But now what's the probability that our average roll is 2 or less? I don't know, but it's going to be very small because it's very unlikely that 20 rolls on average will all probably be smaller than average to get me this average roll of 2 or less. Very, very unlikely that we're going to see something like that happen. So it's not quite clear, but maybe we can go ahead and note and come up with a way to compute this here. So these are some same takeaways that we took from last lecture here. It seems that we think that our sample average should be the same as the expected value of x, which is what we call here mu. The expected value of x, mu. It seems that we think the standard deviation of x bar's distribution should be less than that of x. It should get smaller as our sample size gets larger. The more things we sample, the harder it is for them as a group to deviate from the average, all in the same direction. So the central limit theorem is going to say that as our sample size n gets larger and larger, our sample means will follow a normal distribution. And the normal distribution will have a standard deviation that gets smaller and smaller as our sample size gets larger and larger. So one die is distributed uniformly with a lower bound of A and an upper bound of B. But the average roll across many die is not uniformly distributed. If you roll even just 2 dice right away, it's not equally likely that you roll a 5 or a 6, right? We've immediately lost our uniformity as soon as we go to just even 2 dice. And this will give us a very good approximation of how we should expect our average roll. So super importantly, notice we're describing a different variable here. This describes x, one roll. This describes x bar, the average of n rolls. We're not describing the same thing. It's not like x transformed into a different distribution for x. This is x's distribution, one roll's distribution. This is x bar's distribution, the average of many rolls. If you get an average and another person gets an average and another person gets an average, we would see our averages distributed. If we all made a histogram of our averages, it's going to end up looking normal rather than uniformly distributed here. So it looks like what we need to know is we need to know what would an average roll be in a uniform distribution. What would a standard deviation of a roll be in a uniform distribution? It looks like we need to know the standard deviation and average of a uniformly distributed variable. We have seen the average before, and what we can think is if something's going to take you a uniformly distributed amount of time between 0 and 10 minutes, then hopefully you're very okay with the fact that our average amount of expected time then should be 5 minutes. It's always going to be halfway between the two. Halfway between the two should be the average. The average of A and B would be our average expected time here. Standard deviation, much less obvious of a computation, but I'll give that for us here. So if we are given a uniformly distributed variable, we will see that the average value that that thing takes on is literally the average. Add up A and B and divide by 2, right? So if I said something's going to take me between 0 and 10 minutes, uniformly distributed, 0 plus 10 is 10, divided by 2 is 5. The average amount of time it'll take me then is 5 minutes. Standard deviation, as I said, less obvious. These ones are never super obvious as to where these come from. Again, just go to grad school for finding out where these come from right here. You should notice that there is a slight difference here. There's a little bit of a difference in how we compute standard deviation of uniform variables if we are continuous versus discrete. I think I've set us up with a scenario today for one of each of these will get used right here. So we'll identify when these crop up. And this is just a formula that we're just going to directly use to compute a value of interest right here. So I don't want to talk about these too much, but we will use both of these here. So for our 6-sided die, here's what we have then. For our 6-sided die, we have that our average values here are going to go from a I suppose this is going to be our, oh no, that's still the same thing right here. So for our 6-sided die, let me kind of write some of this stuff right here. Can I get a little bit, can I get a little room right here? Whatever. So here we're starting with x is uniform 1 to 6. So first, I'm going to compute mu sub x. Mu sub x is 1 plus 6 over 2. That's 7 over 2. That's 3.5. And you can see that 3.5 is sitting right there. There's our mu sub x computation. To get our sigma sub x, I can see that we are in a discrete uniform situation. Let me just do this. Okay. For a uniform distribution, if we are discrete, this is our computation for sigma sub x. And so it looks like in this case, we're going to get the square root of b, our upper bound is 6, minus a, our lower bound is 1, plus 1 squared minus 1, all over 12. And that should be the square root of, so minus 1 and plus 1 cancel. That's just going to be 6 squared minus 1 over 12. 6 squared is 36, minus 1 is 35. And if I go to my calculator, I can do the square root of 35 over 12, and that's going to give me 0.1708. 1.708. I think I said my decimal in the wrong place right there. And so you can see that's my sigma sub x right here. So One thing that's happening here is this is just the general standard deviation of any uniform variable that goes from A to B. Here, when we are looking at our sampling average, we also will then need to divide by the number of dice that are being rolled in our grouping right there, square root of n. By the way, I want to come back real quick and show that we're going to get this matching results out here. So we're getting 1.708 right there. Check out, let's come back to this guy real quick. When we roll 100 dice, then I can get the standard deviation of 100 rolls. I'm getting 1.1706. We got sigma sub x divided by square root of n is equal to 1.708 divided by square root of 100, and 1.708 divided by square root of 100 is getting us 1.709. So look at this. The standard deviation of our 100 rolls, we got as our sample, right? It could vary a little bit, a 1.7 or 0.1706. When we use our formula that I just showed you right there with the standard deviation sub x, we got the 1.709. Here we had our n was 100 observations right here, so I divided by the square root of 100, and we got 0.1709 instead of 0.1706. So that's good. It looks like these are definitely matching right here. Of course, this is out of a sample, so it's always going to be have a little bit of variability in there. But this makes me feel very, very good that what we're computing here is correct. This funky sigma sub x divided by square root of n does seem to be in agreement with what we're getting out of our observations that are out there, our rolled dice out there. So this makes me feel good. This matches with, what, 500,000 dice rolls agree with the formula that we just came up with. So that makes me feel better about this kind of funky formula right here. So back to our questions then. So what I want to now do is I want to look at 3 examples to show when do we use the central limit theorem, and when are we not using the central limit theorem. And in all 3 of these cases, we're going to look at a computation of an individual and a group. So this should be your key for computation for this week. The rest of the stuff we're talking about this week is not computational. So I'm going to give you guys a bunch more Excel questions about probabilities, and it's going to be a bunch more about you identify the scenario and you identify if we're talking about groups or individuals here. So let's use, and by the way, I do want to just say I will be scrolling back up. In fact, here's what I should just do right now. I'm going to give myself a box so I can come and find this later. I know I'm going to need this, so I'm going to just box it so I can find it easier later. We will come back to using that value here. So the first example we should look at here, I need to give, what's going on here? Come on. Okay. Did I not delete these? No? Okay, here we are. So I want to kind of talk through what the examples are going to be before we do them, and then I just want to look at them all as a group here first. What are you doing? Okay, so 3 examples. All 3 examples are going to be set up the same way. I'm going to describe to you either a normal, a uniform, or a binomial experiment. In all 3 examples, I'm going to ask you a question about an individual, one adult male, one morning at the bus stop, one play of a game. I'm also then going to ask you a group collective question, a random sample of 25 adult males, a random sample of 30 days of waiting for the bus, a random sample of playing a game 40 times, right? So in all of these questions, the first question is going to be about an individual in which we don't need the central limit theorem. In all of the part 2s of the questions, we are going to be asking how is an average distributed, and so we do need the central limit theorem to talk about groups of averages collectively here. So the important thing is that I think it's natural for us to expect that normally distributed values will have averages that are normally distributed. What's less obvious is that uniform values on average are normally distributed. Binomial values, when you take multiple of them on average, are going to also be normally distributed here. So the central limit theorem says in groups, everything boils down to being normal, even if it's not normal in its underlying distribution here, right? So let's take a look through all three of these, and we'll see all of our computations that go with each of these guys in Excel. So, and I'm going to give myself I'm going to just might as well give myself a whole page for each of these guys right here. I know I'm going to end up writing way more stuff than I always think that I'm going to. All right, so first example, starting with a parent distribution that is normally distributed here. I want to draw some pictures for each of these guys. So here's what I'm seeing first. First thing I want to say is this. Come on, pen, I just don't understand why some days it does it, and some days not allowed. Oh, not allowed again today. Nope, no pen. No pens allowed today. We'll just do it without it. Why that's so hard? Okay, so we've seen this distribution a bunch of times, but it's really important for us today that we talk about our notation of our distribution. Our individual x is normal, our average mu, and our sigma. Average is 68, standard deviation is 2.5. When we go to transition this guy into a group sampling distribution of the sample mean, then we are going to see x bar is going to instead be distributed normally. It's still going to have an average of 68. That's going to stay the same. But now we're going to get sigma over root n right here. So I'm going to get my 2.5 divided by the square root of our sample size, whatever that's going to be right there. So these are the pieces of information that we'll use for this guy right here for our first and second question. So since I know that we're talking about normally distributed stuff, by the way, I'm going to be responsible and I'm going to draw my diagram right here, our bell-shaped curve. I know I'm centered at 68. I know that I'm going to go 2.5 in each direction here to get each standard deviation. So I'll draw, two standard deviations, I guess, in each direction at least. 65.5, 63. So what I'm thinking here is this. We are interested in the probability that an individual is between 65 and 66 inches. And so that looks to me like being between 65 and 66 inches. We're looking for like this little sliver of area right here. That's our answer. Right? So it shouldn't be too terribly tiny, but it should be not a huge amount of area in there, right? So what I'm thinking is this is our cumulative probability up to 66 minus our cumulative probability up to 65, right? I know that Excel is always going to give me my left-hand computations here. And so I'm going to notate this a very slightly different way here. No, I'm not. I'm just going to say this as this should be our norm up to 66 minus our norm up to 65, right? This says accumulate the normal probability all the way up to that height of 66. That'll get us everything up to this right edge. Then chop off all the probability that goes up to the left edge right here. And so if I do this in Excel, let me pop over to Excel now. Let's do our first Excel computation here. In Excel, over here. All right, here we are in Excel. Why is my window so weird? Let me fix for my... Oh, that actually worked out pretty good. Okay. Huh, okay, cool. We're actually right where I wanted. Okay, so here we are. We got Excel. We've got adult male height here. Probability that we're between 65 and 66 inches is going to be our probability that 65 is less than x is less than 66. And here I can do my we'll do equals norm.dist. I want my upper bound for x to be 66. Our mean is 68. Standard deviation 2.5. Cumulative always true for our continuous distributions. We're going to subtract off from this the probability of going up through 65. So this will leave us just with that sliver in between. So the only thing that changed here is 66 is the upper bound to 65 being the upper bound. This will give us between 65 and 66. And I'm going to go ahead and compute this here, and I'm getting a little under 10% as my thing right here. That was pretty close to what I was guessing. Not tiny amount of area, but not a massive probability right there that we saw from our picture. So I think I can say this as to 4 decimal places, 0.0968. So let me go back over here, 0.0968. And then we can convert that to a percentage to 2 places, 9.68%. All right. Now, this is just one individual here. Now what we want to ask is, if we instead sampled 25 people, what would be the probability that we'd see between the 65 and 66 inches? Well, what I'm thinking to myself is it's a lot harder for 25 people as a group to deviate from average than it is for just one person. So I'm expecting my results from sampling 25 people to be much more packed up around that 68 in the middle and much less in the tails. So I'm expecting to lose some probability. I think it's going to be more rare that we see 25 people all be a little bit shorter than average than just to see one person be a little bit shorter than average here. So now what we need to do is we now need to look at our X bar distribution, our distribution of sample average across 25 people. So this should be normally distributed. We should still have an average of 68, but now we're going to see that this 2.5 from our parent distribution is going to get smaller by this square root of the number of people per sample. And this one we're sampling 25 people. So I'll like do my work here in my distribution notation. Square root of 25 is 5. And so it looks like here that we now only have 1/5 as much deviation. We only expect to see 1/5 as much deviation as before. So now I can go ahead and again redraw my picture here. My picture is going to be quite a bit different. We're still centered at 68, but now my deviations are only 1/2 of a unit. So 68.5, 69, 69.5, 70. And I can go the same in the other direction here. 67.5, 67, 66.5, 66. And I mean, if I'm really going to keep going here, you know, 65.5, 65. We're seeing here that we're getting this real tiny bit of area over here now. This is very, 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 very close to the x-axis. I'm expecting that we're accumulating little to no area right here, right? This is going to be a very tiny amount of area that's associated with this. We are 1, 2, 3. We're between 4 and 6 standard deviations below normal. Below average right there. So I expect this to be a really tiny, tiny probability here. So again, I'm going to do my same idea here. Norm for 66 minus the norm for 65, but we now have a different standard deviation term that we're using because it is a standard deviation associated with the sample average of 25 people at a time. It's hard for 25 people to deviate as a group compared to one person. So now when I come to make my probability computations, I'm still looking at the probability that are, I guess I got to call it now X bar is less than 66 because we're now looking to see what the probability that our average is between 65 and 66, not an individual. So now I'm going to go ahead and do the same type of thing here. I know what I should be doing here. I should be inserting a row here, removing that row, and now we can say x bar is distributed normally with a 68 comma, and here we get 2.5 divided by square root of 25, which is normal. 68, 2.5. All right, so here's really my statement of interest for this guy right there for our new distribution, the sampling distribution of the sample mean. And so now I can go back into typing into this guy norm.dist, and now we are looking at, oh, come on, just, okay, I'll just start over. Holy cow, Excel, sorry to upset you there. Equals norm.dist. Our x value, our upper bound x value is 66. Our average is 68. Our standard deviation, though, now is much smaller. Oh man, I typed this wrong over here. Our oh, come on, I just want to be able to fix something ever. Okay, here we go. Third time's a charm. Norm.dist. Our x value of interest. Oh my gosh. Okay. Now I'm typing over here, and we're all actually looking over here, and Excel is not going to do anything dumb to me. I needed to make my statement. Here that we're using a new distribution now for this guy. In fact, what I really almost should be doing is putting this guy right here. The distribution of an individual is that is normal with a 68 average, 2.5 standard deviation. The distribution of the sample means, x bar, is normal. Average is still 68, but we get 2.5 divided by the square root of 25, which gives us the 68.05. So this is now the distribution that I'm using to compute probabilities associated with samples of 25 adult males. So now we can do norm.dist. 68 is our upper bound for the x bar. 66 is the upper bound for x bar. 68 is our average. Standard deviation is 0.5. Cumulative is true. And we're going to chop off from that the area going up to 65. It's the exact same diagram as before, but we can see that we're much more out in the tail now based on the standard deviation having gotten a lot smaller. And this is going to give us something that's, seriously, oh, I typed norm instead of norm.dist. Didn't like that. And now see that it's giving us this slightly wonky looking thing right here. This is our same thing as 3.167 times 10 to the negative fifth. And so this should be 0.123433167. So notice I moved the decimal place 5 units to the left. And so therefore this should be 0.003167%. So this is saying to us it's wildly unlikely that we are going to see a group of 25 adult males have this average height, because we would basically need all of them to be shorter than average. And that's just very unlikely that you're going to randomly select 25 people and get 25, and out of 25 of them, most all of them to be shorter than average, enough to drag the average down as much as it did right there. So difficult for groups to deviate collectively right there. So you might see some of these E's in here. It's almost always, in our case, is going to be referencing tiny numbers. E with a negative number means really, really small stuff out there. This is telling you, this says 5 decimal places to the left. You know it's to the left because it's a negative 0.05 right there. So back to Microsoft Word over here. 3.167 times 10 to the negative 5. That's 0.1234367. That is 0.003167% chance. 0.003% chance that that's going to happen out there. Pretty hard for 25 people to collectively deviate from the mean. The only thing I want to say about this one before I walk away is this. 25 people, that's pretty low on the lower bound of times where we should actually be using our sampling distribution stuff from the central limit theorem. Remember that the central limit theorem really relies on there being a minimum number of people for the central limit theorem to take effect. We can't just go doing this with groups of like 4. As we saw in the code that I showed, things haven't quite shaped up to be normally distributed yet if you have very small sample groups. So that was our normal distributed one right here. We changed from an individual having a distribution with a standard deviation of 2.5 to a group of 25 people still being normally distributed, but with a much smaller standard deviation, giving us much smaller tail probabilities and much more probabilities centered around the middle right there. So our next example here. Now we're going to look at an example where we see this uniformly distributed variable. The times that a bus near my house arrive in the morning are uniformly distributed between 8 and 8:15. So what I want to know is, first, what's the probability that on one randomly selected day the bus comes after 8:10? So we're only looking at one observation, so we don't need any of the central limit theorem stuff. The second question is going to look at the average over 30 days. So that is a group average. That is a sampling distribution of a sample mean. A sample mean is a sample average, just the average of 30 days, for example. So we are interested in what does the sample mean look like for the second one. If we take a sample, what's the mean going to be? In this first guy here, we've got that x is distributed uniformly. I'm going to notate my times as just minutes after 8 o'clock. So this will be 0 minutes after 8 o'clock up to 15 minutes after 8 o'clock. That's between 8 and 8:15. So what's the probability that on a randomly selected day the bus comes after 8:10? Well, I'm just going to use how I know to compute probabilities with a uniform distribution, which is draw a picture and compute it. So I'm noticing here that we are looking at 0 to 15. I should have a rectangle shaped distribution right here. Since this width right here is 15, it must be the case that this height then is 1/15. So that 1/15 times 15 gives me the total area of 1 that's going to be underneath the curve. I am interested in the probability that this guy, or that the bus, I'm still thinking about my furnace person that hasn't shown up yet. I'm wondering about the probability that the bus shows up after 8:10. And so we can just look for this area right here of a rectangle. This is from 10 to 15. This is my height of 1/15. This is my width of 5, it looks like. And so this should be 5/15, also known as 1/3 or a 33.33% chance. Right? So this is a 1 day probability right there. On 1 day, after 8:10 would be 1/3 of the minutes that are available from 8:10 to 8:15. And so there's a 1/3 chance of that occurring right there on 1 day. But what we're thinking is that on average over 30 days, it's very likely that we're going to see results that are much closer to the average arrival time for this bus right here. So what is the probability that over 30 days, the average bus arrival time is after 8:10? Well, this is now looking at the average over 30 days. So this is what's telling me, well, we're now looking at the distribution of average times. And since 30 is at least 30, the central limit theorem applies, and we can go ahead and upgrade this to being our distribution of the sample mean. X bar is the sample mean. This is its distribution. It is normal, where we're getting our average from the X distribution, and we're going to get our standard deviation also from the X distribution, and we're going to divide by the size of our sample. Mu X, sigma X come from parent distribution X unif 0.15. So I'm going to have to do some scrolling back up here to see where our values come from. We need to compute mu of x and sigma sub x for a continuous uniform distribution here. So I think the mu sub x is easy. For the sigma sub x, we're going to have to look back up at a formula. The mu sub x, we said, was just the average, right? So if it's going to come uniformly likely anytime between 0 minutes and 15 minutes after the hour, then I should expect right about halfway in between is going to be our typical result. Halfway in between 0 and 15 is 7.5, but we can see this by averaging them right here. 0 plus 15 over 2 is just 15 over 2, and that is going to be 7.5. So on average, the bus should be coming 7.5 minutes after the hour. That's our average return or arrival time. Mu sub x, or that's the wrong one right there. Sigma sub x, I've got to look up for this formula right here. I never remember this formula. This is certainly one that you should just be keeping a reference for. If I scroll up right here, I can see this formula now. In our case here, are we continuous or are we discrete? Here we're looking at just an arrival time that the bus is coming at. It's not some fixed number like the rolls on a die. So I think we're using this continuous formula right here. Notice that for the rolls of the die, we used our discrete formula that had the extra +1 and -1 in it because rolls of a die are discrete. Bus arrival times are continuous. So I'm looking at my square root of b minus a squared over 12. Square root of b minus a squared over 12. Oop, I don't know why I put a, just get rid of those two parts. And here we can then say this should be the square root then of 15 minus 0 squared over 12, which is the square root of 15 squared is 225 over 12. And if I go to my calculator for this guy, I'm going to get a square root of 225 over 12, and I'm getting 4.330. By the way, I would like to ask that all of us keep at least 3 decimal places on all of our standard deviations out here. These little bits are going to end up making a difference, especially as these numbers get smaller and smaller. So notice here, this is just the standard deviation of our original variable x. Since we are looking at an average of 30 days, we still need to divide by the square root of n. So we're still needing to get our sigma sub x over root n in this case. This is going to be our 4.330 over the square root of the 30 trials that we're doing here, the 30 days that we're considering. So I'm now going to divide this guy by the square root of 30 as well. And I'm going to get here a 0.7906. 0.7906. So here's where we're at. We have now figured out that the average time for the bus to arrive over 30 days, if we average our results over 30 days, come on, I just, oh yeah, that's why. Then now we're going to see that our results are no longer uniformly distributed like they originally, the individuals were. We now will have a sampling distribution, a distribution of the sample means will be normally distributed. Our average is the average of the original distribution, 7.5 minutes after the hour, with a standard deviation of 0.7906 minutes above and below the hour right there. So about 0.8 minutes right there, right? So notice now we're interested in the bus arrival time being after 8:10. Well, let's just even see how many standard deviations is 8:10 from average in the sampling distribution. Well, we can compute our z. We used to have x minus mu over sigma. We now have that z is x bar minus mu over sigma over root n. And so in this case now our x bar would be 10 minutes 10 minutes after the hour for the average time, minus 7.5 is the average time for the bus to get there. And we computed sigma over root n to be 0.7906. And I can now check this out here. 2.5 divided by that decimal, 3.162. So you should notice right away that we are interested in computing the probability of an event being at least 3.162 standard deviations above normal. Right, there we are out there at 3 standard deviations. We know from the empirical rule that the middle 3 standard deviations cover about 99.7% of all of our responses. So we are taking the remaining 0.3% out in the tails, splitting it up equally into equal tails. So we're getting 0.15% and 0.15%. And then it's actually even a little bit less than that because we're not just 3 standard deviations, we're 3.162. So I'm expecting to not even get 0.15%, but maybe something like 0.1% is my answer right here. Estimating this from doing a little computation and a little bit of empirical rule action right here. So notice here that we are interested in a right area, a right probability here. So I am going to take 100% of my probability, and I'm going to chop off the stuff to the left of that that's associated with our x value of interest here. And so to do my computation here, I am going to do equals 1 minus the normal distribution computation associated with, and by the way, here I can either do this 10 minutes or the 3.162. By the way, I'll do both of these in here so we can see it. They're going to match right here. I can either do this with in context with X or out of context with Z. So let's go pop over into Excel and do each of these guys. Actually, let me just leave this here. So over in Excel. So first things first. Let me move those guys down. So in our first case right here, the probability the bus comes after 8:10 on a single day. This one's easy. I don't even have to use Excel for this guy. I just go out to 15, draw my box right here. That's at 15. Our 10 and greater is going to be, this is 10, that's 15. This is a height of 1/15. And so we're getting 5 over 15, which is just 1/3 right there, or 33.33%. That the one time the bus will come 10 minutes after. Now, on average, over all these times here, we're going to get our X bar. X bar is going to be normally distributed with an average of 7.5 and with a standard deviation of, and what did we figure out our standard deviation was here? We got 0.7906, 0.7906 divided by the square root of 30. Which we ultimately found to be, oh wait, no, sorry, I got ahead of myself. 4.330 is what I was looking for there. Let me fix some of these. 0 right there. And this was really our, okay, now that looks right. We computed the standard deviation of the original x variable to be 4.330. We divided by the square root of the 30 trials that we're doing, and we landed at this normal distribution right here. So now we are interested in the probability. Why am I slid over here? We are now interested in the probability that our x bar is greater than 10. So that should be 1 minus the probability that x bar is less than 10. And for that, we can go to, should be equals 1 minus norm.dist. Our x value of interest is 10. Our mean, 7.5. Standard deviation, 0.7906. And cumulative is going to be true right there. And so we were guessing something like 0.1%, and I'm seeing 0.07%. Why do I feel like I set this up like a little... Oh, okay. There still are 3 standard deviations from normal. And we can verify that we did this z work correctly right here. So we had otherwise found that we could do, let me give myself a little more space here. Alternatively, we could do that our, find that x bar equals 10 is the same thing as z being equal to 3.162. And so we could also do the probability that z was greater than 3.162, which should be equal to 1 minus the probability that z is less than 3.162. And notice this is a time where we could use our standard normal in here. I'm going to do norm.s.dist because this is standard normal. In this case, it only wants z from me. And that's all I got to enter in there is just the z value and true. And, oh, I forgot to do my 1 minus in here. And you should notice we're getting essentially the same things right here, 783, 783. It's got a tiny smidge of error in there, but that's just because I rounded when I computed my z value right there is the only reason that's coming up. And so it looks like our response right here, if I move this decimal place over 2 places, then I'm getting a 0.078% chance. We were thinking a 0.15% chance, except a little bit less. So I said about a 0.1% chance. And instead of 0.1, we got 0.07. So I was pretty dang close to this. This is pretty close to that 0.1% that we were kind of guessing at right there. And that made sense. I could see it in my picture before I even did it there. All right. So here are our Excel computations. And by the way, again, I'm going to post this in here and notice that you can, for example, click on this and see exactly what I have typed in up here for any of these, or just double click it and it'll bust out exactly what's written in there. So I will post this and you can use this guy as your reference out there. So let's look at one more example here and we'll call it a day. So coming back over to Microsoft Word here. Our final example is going to be, let's start with a binomially distributed variable, and again, see what happens when we do this with groups. So in this binomial scenario here, we're going to play a game. In the game, you flip a coin 15 times and report the number of heads. So in this game right here, it looks like we are, x is binomially distributed. Let me just write this where this sort of goes right here. In the first case, we're only going to play the game one time. Because we're only playing the game one time, I know that I am not using my central limit there. I'm just using my regular binomial probabilities here. So here we would say x is distributed binomially. We know that this is always NP, right? So we have here that x is binomial. Now notice here, one binomial experiment, we really have two different sample things going on right here. We've got the 40 times and we've got the 15 times. One game results in you flipping a coin 15 times. That's our number of flips for n. The probability of a success on any one flip, a heads, is 50%. I don't know what that stuff is right there, binom. 15.5 right there. So I'm interested in the probability that I'm going to get fewer than 9 heads. I'm going to be smart and remember that with my discrete stuff here, that this should be really less than or equal to 8, because I know that Excel does include my boundary of 8, so I need to include it. If I use 9 as my x value in Excel, it would really give me the probability that x is less than or equal to 9, not just less than 9. And real quick right here, we should notice that what's our average in this case? How many heads do we expect to typically get? Well, NP is our expected value in a binomial distribution. And here, N times P, half of 15, is 7.5. So when I'm saying what's the probability that I get less than or equal to 8, I'm thinking this should be really close to 50%, because 50% would be when we do x is less than or equal to 7.5, right? So it should be a little bit more than half. Maybe some 50-60%, something like that. A little bit more than half is what I'm expecting here. And so I think I can just do here my binomial stuff associated with 8 in Excel here. So let's pop over to Excel and do that one. So if I go over to Excel, then here we can say that that x is distributed binom 15.5, and therefore the probability that x is less than 9 is equal to the probability that x is less than or equal to 8. And so I can then say this should be equal to then our binom.dist. My number of successes is 8. Trials is 15. Probability of success, 0.5. Cumulative, yes, we want the probability for up through 8 successes. And as we guess, we're going to guess a little bit more than 50%. This is a little bit more than 50% than I was expecting, but that's okay. This is still what I was thinking there. Not outrageously more than 50%, but more than 50%. So I'm seeing here a 69.64% chance that we will get less than or equal to 8 heads if we flip a coin 15 times. But now here's the difference. Now I'm going to play the game 40 times. One play of the game is 15 flips of the coin. So this is going to be 600 total times I'm going to flip this coin here. One game is 15 flips. I want to know not about how many times I won or anything like that. I want to know what my average number of heads was per game. It's going to be really hard for me to have some extreme number of heads, right? If I flip a coin 15 times and get 10 heads, not weird at all. If I flip a coin 15 times and then do that 40 times and I get my average number of heads to be 10 out of 15, that would be crazy across 40 trials. That would be wildly unlikely because it's typical that our averages should move towards the middle right there. So it's hard for us to see extreme events with groups. So now, let me pop back over into Word right here for one of our last few switchovers here. We're now going to see that since we are doing this 40 times, that we should be seeing our average number of heads should be distributed according to a normal distribution, with the average associated with our original and with our standard deviation associated with the original divided by the square root of n. So, and again here, mu sub x, sigma sub x come from the parent distribution. So we have to know where to get mu sub x from and sigma sub x. So in a binomial distribution, we've already talked about this. The average is n times p, and the standard deviation is npq, the square root of that, square root of npq. So in our case here, our mu sub x should be number of flips per game is 15, probability of success is 0.5, half of 15 is 7.5. This says you should expect to get 7.5 heads out of 15 when you flip a coin 15 times. Our standard deviation here is going to be the square root of npq. That's 15 times 0.5 times 0.5. Or sorry, those are points right there as well. Man, I'm just going to rewrite that. That just looks difficult to read right there. This should be 15 times 0.5 times 0.5. That should really just be a quarter of 15. So square root of 3.75 and square root of 3.75, 1.9365. And so with these two pieces of information together, we can determine that the distribution of the average of our rolls should be normal. It should be centered at our typical average of 7.5 heads, but it's going to have this smaller standard deviation now of 1.9365 divided by the square root of 40, because we're going to do 40 trials here, right? So this should now be giving us x bar is distributed normally, 7.5 is the average, and this number divided by the square root of 40, 0.3062. So we can now use this normal distribution right here. This is our distribution of the sample mean, the sampling distribution of the sample mean. And I can now compute things like what is the probability that we're going to see. And by the way, I'm going to do this one the both ways way right here. Let's compute a z-score for this guy real quick. Our z-score should be x bar minus mu over sigma over root n. And so here we are interested in seeing 8 or fewer, right? Our average to be 8. 8 minus 7.5 divided by this 0.3062. And that's going to be 0.5 divided by that decimal down there. So 1.633. So this says to see a result that is like getting an 8 as your average over 40 times of playing this game, this should then be saying that's like getting something about 1.5 standard deviations above normal. So that says to me that we're interested in all this area. All right, this is all of our probability of interest. Having an average roll of anything below about 1.5 standard deviations above normal, right? This is 1.6 standard deviations above normal. So there's my 1.6 standard deviations above normal. We're interested in all this area right here as being our answer. What's the probability that we see anything less than that out there? So I can either phrase this as the probability that x is less than or equal to 8, or I can phrase this as the probability that z is less than or equal to 1.633. And let's do both these in Excel, and we'll call it a day. So switching back over to Excel for our last one right here. We have already done this guy right here. So let's phrase this one up both ways now. So now we're going to see that x bar is distributed normally. NP and square root of NPQ are our two terms there. And that got us a normal of 7.5 and square root of square root of NPQ. I've already said it wrong here. Square root of NPQ over square root of N. And that should be 7.5, and what do we get? 0.3062 for the other term. 0.3062. So now we've determined what is the distribution, the normal distribution that describes the sample means. And so now I can go ahead and find either the probability that x is less than or equal to 8, and that should be our norm.dist. My x value of interest is 8, my mean is 7.5, my standard deviation is 0.3062. Cumulative, yes, always for that one. And here we're seeing, as we guessed from our image right there, a vast majority of our area. When I say our image, I'm picturing this diagram down here. It certainly looks to me like there's some amount of area that we didn't include down there. Totally believable to me that's about 5%. We've got the other 95%. There's a 95% chance that over 40 games, your average roll will be less than or equal to an 8 right there. And I do just want to say, just for one last one right here, we determined, I've got some vaguely wrong words in here, x bar. We computed that x bar being equal to 8 gave us a z score. That was 1.633. It was a 1.633 standard deviations above normal. And so therefore we could also do this as z, the probability that z is less than or equal to 1.633. And over here I can do this as equals norm dot s, because it's standard normal. It's z stuff, so it gets the s, norm dot s dot dist, and it only wants z from me, 1.633. True? Yep. And notice we're getting that same response right here, so it looks like our final answer here is this 94.88% chance that we will see an average roll of fewer than 9 heads over 40 games. Much, much, much more likely that we're here near the middle of our distribution, since less than 8 was sort of an upper tail for our distribution, and more things were packed up towards the middle. We got much more of our area got covered here, because the larger and larger and larger our sample size gets, the more and more likely it is that our sample is closer to average, what we expect right there. So this is good. So we went through way more Excel stuff right here, and kind of when to use and when not to use our central limit theorem idea with getting a sample mean of a sample distribution. So I am hoping that these last couple pages right here are the very, very useful for you examples to see for your upcoming homework. We should be able to now compute probabilities associated with individuals that are normally distributed, groups that are normally distributed, individuals that are uniformly distributed, groups that are uniformly distributed, either continuous or discrete. We got our two different formulas up there and boxed in red. And our individuals that are binomially distributed, as well as our groups that are binomially distributed here. So we can do individuals and groups now for all three of our major distributions here. The reason that this is going to matter is because starting tomorrow, we're going to start trying to make our decisions based on the statistics that we compute here. So we want to do things like say, was that really that unusual, right? Was that so unusual that maybe our original information was wrong, right? And again, I think coming back up here to our um, to our height example right here, this example right here is a great example of where we're headed. If I ever observe something to be this unlikely, I have to think that there's something that went wrong, right? There's how many things in your life have you ever observed where there is a 0.0000000000077% chance of that thing happening? Probably very, very, very few, right? So this is maybe instead evidence to me that we had some wrong information to start with, rather than that our observation was just unlucky. And what we are going to start doing now is now with all these probability computations, we're going to start saying things to ourselves like, how weird was that? Is that so unlikely that I must have kind of, in a sense, done something wrong? Or is that just the luck of the draw on that one and we drew a very strange sample? We're looking to start making some decisions now based on the statistics that we've been computing. And so that's kind of where we're headed now. We'll be able to do that with our sampling distributions of our sample means. So we're going to pick this up with chapter 9 for tomorrow's video. And so tomorrow we'll get sections 9.1 and 9.2. And that'll do it for us for then our week 8 items right there. So be sure that you are a master of computing all of the probabilities that we need to compute now associated with both our individuals in the uniform binomial and normal distributions, as well as understanding that we can compute averages and standard deviations of our baseline variables and use those to help construct our sampling distributions of the sample mean out there. All right, that wraps it up for today. I will see you guys next video for our introduction to chapter 9, and we'll begin our decision making with statistics here. We'll see you guys next video here. Oh, infinitesimal prints. No, I did not, by the way, but I'm going to. I just haven't done that yet. Yeah, I'm going to do that here and get the affiliate things happening. All right, I'll see you.